Hi everyone, this is Eve from the University of Warwick. Now I will share my work in the International Conference of Computer Vision 2025. The topic is about adversarial training for probabilistic robustness. First, I will introduce the main difference between two typical types of robustness, which is worst-case robustness and the probabilistic robustness. Most of the adversarial training is focused on the worst-case robustness. They are trying to find some adverse examples within a specified numbers. With those adverse examples have the maximum loss. Then training with those adverse examples can improve the adversarial robustness. And but a more practical view of robustness is the probabilistic robustness, which refer to the proportion of adverse example. They can tell how robust a model is when and whenever a adverse example is found, especially when the model is large. The proportion of adverse example within a small number region is more relevant and is more important for models' real-world applications. So in this work, we will focus on the probabilistic robustness, and we will introduce a new training algorithm which can improve the probabilistic robustness. Here I will introduce the loss landscape based on those two type of adverse example, those two type of robustness. Most of the time it's about the case one. As I said, for the worst case robustness, they're trying to find those adverse example which have the highest loss of this model. So in loss landscape, those adverse example usually locate in the tall and tight peak in this loss landscape because they have the highest loss. Then training with this adverse example can improve the model's ability to those worst attack. But for probabilistic robustness, they are trying to calculate the proportion of adverse example. So most of the time, the adverse example will locate in the widest peak of loss landscape because within this location, they can cover more adverse example. And the training with those adverse example can decrease the proportion of adverse example. Then therefore improve the probabilistic robustness. Also, there's another cases, which is the case two. In these cases, which means we can find some adverse examples that can improve both worst case robustness and also probabilistic robustness. Because in these cases, the adverse example usually can locate in the highest and widest peak of loss landscape. So based on the loss landscape description, we designed a new algorithm, which we called AT-PR, and we designed those three-step algorithm to training model, then to improve their probabilistic robustness. So here is the detail of the algorithm. The first step, we aim to generate a set of diverse adverse example within this small number. And we will also use the project gradient descent algorithm to generate those adverse example candidates. And the step two, we will perform gradient descent search methods to calculate the distance between those, calculate the distance of this adverse example to their corresponding decision boundary. Then, because within this distance, within this region, we said there are all adverse examples. Then finally, the step three, we will pick the adverse example which have the largest distance to their decision boundary. Because those adverse example, if they have the largest distance to their decision boundary, then they can cover the more adverse example, which means in the loss landscape, those other adverse example will locate in the widest peak of this loss landscape. So training with those adverse example can decrease the proportion of adverse example, then improve the probabilistic robustness. Here are some experiment results of our AT-PR. Here we just give those three tables. From table 1, we can see our AT-PR can achieve the best probabilistic robust performance compared to those adversarial training method designed for those worst case robustness. And also, they can achieve a better trade-off in model generalization. They can have a higher, which means they can have a higher clean accuracy. Also, table 2, we prove that we can combine our AT-PR with other advanced adversarial training method like trees, and it can also achieve the best clean accuracy and probabilistic robust performance, even on large models like vision transformer. Also, table 3, we compare AT-PR with other advanced adversarial training method like tree, smart, ALP, or something. So, and the result shows that our AT-PR can also achieve the best probabilistic robust performance. So here is all my presentation. And if I have more questions, you can refer to our papers for more details. And thank you for watching.